Hello, everyone. I'm Masazumi Honda from Yukawa Institute for Theoretical Physics in Kyoto. This is the first precursor video on quantum computation. In this first video, I will give an introduction to this topic and some basics on quantum computation. By the way, these photos are from my Instagram. Now, Kyoto has a beautiful hydrangeas, and we will see. I hope we will see soon directly in some time. So let me start with the introduction. Perhaps you got this news saying that Google claims quantum supremacy 2 years ago. And I'm not sure if this is really quantum supremacy, and it is controversial. But anyway, I got the impression from this news that resource of quantum computer is growing well. And in this lecture, I would like to consider how we can use this progress for practical physics. And this lecture is a preparation for application of quantum computation to numerical simulation of quantum field theory. And there are some motivations. Generic or naive motivation would be, since we hear that quantum computer is very powerful, so we simply would like to use a powerful computer. But there is a specific motivation for our purpose. So as I will explain, quantum computation is suitable for Hamilton formalism. And in Hamilton formalism, we have a liberation from infamous sign program in Markov chain Monte Carlo simulation. So what is the sign problem? Perhaps you already know by some other lectures, but let me briefly explain it. In the conventional approach to simulate quantum field theory, we first consider Euclidean spacetime rather than Lorentzian spacetime, and discretize the Euclidean spacetime by lattice, like this. Then we make a path integral finite dimension. Then we numerically evaluate this integral by some algorithm. And in conventional approach, we usually use an algorithm called Markov chain Monte Carlo method, in which we regard the Boltzmann factor as a probability, and we approximate the expectation value by average over samples. But of course, this approach could be maybe problematic when Boltzmann factor is not real and positive and highly oscillating. So there are many important physical examples with sign problem. For example, when we have a topological term, then the action becomes complex, and the Boltzmann factor is also complex. Also, when we have a chemical potential, fermion determinant may have an indefinite sign, and we have a sign problem sometimes. So when we consider real time, the Boltzmann factor becomes exponential is rather than exponential minus s. So basically, any theory with real time has a serious sign problem. But in Hamiltonian formalism, we do not consider path integral from the first, so we don't have a sign problem from the beginning. And of course, this is quite an unfair explanation of the sign problem. There are already various approaches to the sign problem within the framework of path integral formalism, but I will skip it. But life is not so easy. Instead, there is a cost of Hamiltonian formalism. So in Hamiltonian formalism, we should play with Hilbert space, but quantum field theory typically has an infinite dimensional Hilbert space. So some regularization is needed. And after regularization, we typically have to play with a huge vector space. So in numerical simulation, technically, computers have to memorize a huge vector and multiply huge matrices. But we may hope that the quantum computers in future do this job. So let us consider this possibility. But we hear that the quantum computers don't have a sufficient path yet. So since we are not making quantum computers by ourselves, you may wonder whether we should care this problem now as users. Shouldn't we start to care after quantum supremacy comes? But my personal answer is different. I personally think that there are many things to do, even now in various contexts. Various contexts include numerical stuff, analytic stuff, purely algorithmic stuff, lattice, TH, PH, and so on. For instance, we haven't established how to put QCD efficiently on quantum computers yet, and how to efficiently pick up various real-time physics yet. So I personally think that even we have a quantum supremacy now, we are not ready to simulate QCD by quantum computer yet. Also, so far there is only one example to take a serious continuum limit of the quantum field theory in the context of quantum simulation. So we are now at the very beginning of the progress. And before going to main part, there are some good news. First, if you have a Google or Facebook account, you can immediately use IBM's quantum computer for free. Second, simple code for quantum computation can be made by drag and drop in IBM's website, as I will explain. And serious code is made by Python. And although I'm giving this lecture, I'm beginner of both Python and quantum computation, honestly. I started both more or less 2 years ago. Finally, most importantly, this topic is very fun. So I hope you will enjoy my lecture and class. Here, I finished the introduction. Next, I will explain some basics on quantum computation, and then I will give some demonstrations of using quantum computer in IBM quantum experience. Finally, I will give a summary. In the second video, I will talk about the quantum simulation of the one-dimensional Ising model. Okay, now let's move on to basics of quantum computation. So let me start with what is a qubit? Qubit is a quantum version of a bit. In particular, this is a quantum system with a two-dimensional Hilbert space. The two-dimensional Hilbert space is spanned by 0 and 1, which are simply 1, 0 vector and 0, 1 vector. Generic state is given by a superposition of these bases with a normalized coefficient. And we don't need to mind how it is realized in real quantum computer as users, but one of the simplest realization is given by spin-half system, where we identify 0 to be upspin state and 1 to be downspin state. And there are two operations in quantum computation. First one is acting unitary operator, which maps psi to u psi. And now since we are in two-dimensional Hilbert space, u is simply 2 times 2 unitary matrix. In quantum circuit notation, this is represented like this, and we are going from left to right. And then we multiply u to psi, and then we get u psi. Another important operation is making measurement. In measurement, we get a classical number with some probabilities. In particular, when we have the state alpha 0 plus beta 1, we get c equals 0 with the probability alpha square, and c equals 1 with the probability beta square. Let me introduce some important single qubit gates used in this lecture. First class is XYZ gates, which are just Pauli matrices. X is sigma 1, Y is sigma 2, and Z is sigma 3. In particular, X plays the role of not in logical operation, since this maps 0 to 1 and 1 to 0. And using X, Y, and Z, we can define Rx, Ry, Rz gates, which depend on continuous parameters. Rx, Ry, Rz are simply an exponentiation of X, Y, and Z. Another important gate is the Hadamard gate, which is defined in this way. And this maps 0 to 0 plus 1 and 1 to 0 minus 1. Perhaps you are not familiar with this gate, but this gate is very important in the context of quantum computation. The final gate is T gate, which is a special case of RZ gate. And we can also, of course, a system with multi-qubit. For example, we can consider 2 qubits, which has a 4-dimensional Hilbert space. Then generic state is spanned by 0, 0, 0, 1, 1, 0, and 1, 1. These bases are simply corresponding to these simple vectors. Similarly, we can consider n qubits, which has a 2 to n dimensional Hilbert space. Note that the dimension of Hilbert space is growing exponentially as we increase n. Generic state is simply spanned by these bases. In my lecture, I'm going to use only one 2-qubit gate, which is called controlled X gate or controlled NOT gate. This is defined by these relations, which map 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, 1, 1 to 1, 0. Here is the rule of the game of quantum computation for me. The rule is do something interesting by a combination of action of unitary operators and measurement. Something interesting usually means doing faster computation than classical computer by quantum computer. Next, I'm gonna explain a concept of universality. It is known that any unitary gate is a combination of single qubit gates and controlled NOT. This is often said single qubit gates and CX are universal. For example, there is a 3-qubit gate called Toffoli gate or controlled NOT gate. This is a 3-qubit gate, but it is known that this gate can be written in terms of controlled X and some single qubit gates in this way. It is also known that any single qubit gate is approximated by a combination of H and T in arbitrary precision. And H and T are explicitly given in this way. Therefore, by combining these two statements, we can say that H, T, and CX are universal. Next, let me explain concept of error in real quantum computer. In my explanation so far, I pretended as if a quantum circuit is an isolated system. But in real quantum computer device, this is not true. Namely, qubit in quantum circuit is not isolated system, and there are interactions with environment which cause error or noise. Therefore, we finally need to include quantum error correction, which seems to require a huge number of qubits. And it is known that this is a major obstruction of the development of resource of quantum computer. In this lecture, I will not discuss quantum error correction, but it is known that quantum error correction can be taken into account in independent way of details of the algorithm. Finally, let me introduce a concept of a simulator. As you know, quantum computation is a special case of linear algebra. So the same algorithm can be implemented in a classical computer, but without speed up, since one quantum step is generally corresponding to many classical steps. Simulator is a tool to simulate a quantum computer by using classical computer. This does not have errors, and we can get ideal answers since we are using classical computer. The same code can be run in quantum computer with speed up. We will see how it works later. So, although simulator does not give a speed up by quantum algorithm, but it is useful to test the algorithm and estimate computational resources. By computational resources, I mean number of qubits and the number of gates. Here is a short summary. Qubit is a quantum version of bit. There are some important gates, Rx, Ry, Rz, which are defined by exponentiation of x, y, and z. And there are also important gates called Hadamard gate and Cont'd X. Rule of quantum computation is to do something interesting by a combination of acting unitary operators and measurement. HT and CX are universal, and real quantum computer have errors, and simulator is a tool to simulate quantum computer by classical computer. Here, I finished the section on basics of quantum computation. Next, I will give some demonstration by using IBM Quantum Experience. If you access the web page of IBM Quantum Experience, for the first time, you are asked to sign in by some accounts like Google, Twitter, and so on. Then if we sign in by some way, then we come to this page, and then you can compose a new quantum circuit. Now I'll switch to internet browser and come back to the slide. All right. Now I'm in Google Chrome. Let's access IBM Quantum Experience. So I am not asked to sign in since I have already signed in. And now let us click this button. And I'd like to create new file. Okay. So now we have a 3-qubit system, but I'd like to make it a single qubit system for simplicity of explanation. Okay, so now we have a single qubit system, and the state is initialized to be the state 0. And in this interface, we can make quantum circuit by drag and drop, like this. But first, as a warm-up, let us consider the following trivial problem. The problem is to measure the state 0. So now I have put the measurement get, and the state should be 0, and we can submit the job by using this button. And in this button, first there is a choice of machine doing this computation. There are choices of both simulator and real quantum device. And these are real quantum device. But for the first time, let us submit the job to a simulator. And this is the name of simulator. So let us choose it. And in the second step, we can choose some settings. And in particular, short is the number of measurements. So for this time, let us take 1024 as a default. Then we can submit this job by clicking this button. So let us check the result. Okay, here is the result. This result is saying that we got state 0 for 100%. This is, of course, the trivial result. But next, let us submit the same job to real quantum computer. So we can click this button, but choose a real quantum computer for this time. Okay. So I can choose anything, but for now, let us choose the device in Athens, in Greece. Okay, job is sent, but typically we should wait for a time when we use a real quantum computer. Okay, the computation is done, so let us check the result. So here is the result. So this result is saying that we do not measure the state 0 for 100%. Instead, we have measured the state 1 6 times. So this is a realization of error in real quantum device. All right, next let us consider another trivial problem to measure state 1. This is done by putting X on the qubit. And this symbol is the same as X gate. So by putting the X gate here, the state is mapped to 1 from 0. So let us submit this job to the simulator. And the calculation is done. And of course, we get the state 1 for 100%. Okay, next let us submit the same job to the real quantum computer. So let us choose the one in Athens again. And we may have to wait for some time. Okay, it's done. Let's check the result. Right. So again, we do not measure the state 1 for 100%. For this time, so we have a larger error compared to the previous problem. So again, this is a realization of error in real quantum device. Okay. Next, let us consider the simplest non-trivial problem, having a superposition of a state. So for this time, let us measure H0, which is the same as a combination of 0 and 1 with equal weight. So let us submit the job to simulator. Okay, the job is done. Okay, here is the result. So the result is saying that we got the state 0 and 1 with more or less 50%. But note that this is not exactly 50%. This is slightly different from 50%. This is because we have made a finite number of measurements. So this is not error coming from using quantum computer. Rather, this is statistical error coming from the fact that we are doing a finite number of measurements. Okay. So to make sure this is a statistical error, let us submit the same job with a different number of statistics. So let us change the number of shots. So let us make it 4 times. Here is the result. And you see that this is closer to 50%. So we can improve statistical error by increasing the number of shots. Okay, now let us do the same thing for real quantum computer. So let us submit it to the one in Athens. And I'd like to submit the same job with the different number of shots. Okay, let us wait for a while. Oh, the first one is done. Well, for this time, somehow it's very close to 50%, despite the results should include both quantum error and statistical error. This time sometimes happen. So this is a result of real quantum computer with a larger number of shots. So it's still close to 50%, but you see that the result is not improved very nicely. This is because although we can improve statistical error by increasing shots, but we cannot improve quantum error in this way. Okay, now let's go back to the slide for a while. All right, I'm coming back to the slide. And let me give a short summary on what we have done. So we can make a new quantum circuit by clicking this button. And first, I have considered the trivial problem to measure the state 0. This is simply done by dragging the measurement gate. And then by clicking this button, we can submit the job to simulate our real quantum computer. First, we had to choose the name of simulator or real quantum computer. Then we got this result. And of course, we got the state 0 for 100%. And next, I submitted the same job to real quantum computer. Then we got a bit different answer. And this is a realization of quantum error. And as a second trivial problem, we measured x0 equal 1. Then we got a similar result. In the result of simulator, we got a state 1 for 100%. But we got the error again in the result of real quantum computer. Next, we consider the simplest non-trivial problem by measuring h0 equals this state. So we are now in quantum world because we have a superposition of the states. Then we got this result by simulator. We got more or less 50-50 result, but it's not exactly 50-50 because of statistical errors. If we increase the number of shots, then we got improved result like this. Next, we submitted the same job to real quantum computer. For real quantum computer, we have both errors and statistical errors. So if we increase the number of shots, we get improved statistical errors, but there still remain some quantum error because we are using a real quantum computer. Okay, next let us consider another trivial problem in 2-qubit system. So I'll go to the internet browser again. All right, now we are in Google Chrome again. So next, let us consider the 2-qubit system. So we can click here. Then we have a 2-qubit system. So first, let us consider trivial problem for 2-qubit case, which is measuring the state 1, 0. So let us submit this job to simulator. And this is the result of simulator. So in our notation, we should measure the state 1, 0, since we are putting X gate on the first qubit. But the output is saying it is 0, 1. This is not because our guess is wrong. This is simply a result of notation in IBM. So in IBM's interface, the output appears always in opposite order from our notation for the case. So please be careful for this point always. And similarly, we can put control not get by dragging this button. And now we should get the result. Now we should get the state 0, 0 for 100%. So this is correct. All right, next, let us go back to the slide again. All right, now I'm coming back to the slide. As a trivial problem for 2-qubit system, I considered a problem to measure the state 1, 0. Then we got this result, but note that the notation in IBM's interface is different from the usual ket notation in our field. And we can also put the 2-qubit operation by dragging and drop. These are results by simulators for these 4 problems. So this is just confirming the definition of controlled X. So for the first problem, Cx maps 0, 0 to 0, 0. And for the second, Cx maps 1, 0 to 1, 1, because the first qubit is 1, so we should multiply X on the second gate. And we got a similar result. And here is the result of a quantum computer with 1024 shots. We see that there are some errors like this. And depending on details of quantum circuit, somehow we get a larger error. Okay, let us summarize the first pre-class video. Quantum computation is suitable for Hamiltonian formalism, which is free from sign problem. Instead, we have to deal with a huge vector space. But quantum computers in future may do this job. Rule of quantum computation is to do something interesting by a combination of acting interpreter and measurement. Real quantum computer have errors, so it is very important to make a quantum error correction in future. So this is the end of the first video, and it will be continued to the second video. Thank you very much.